So repeated roots in the characteristic equation are actually really difficult, and we need a whole new technique in order to solve differential equations with repeated roots. So let's go back to second order differential equations, and they'll still be linear, homogeneous, and with constant coefficients, so pretty easy. So we'll go back to this one that we mentioned, y double prime minus 6y prime plus 9y equals 0, and it looks like something we can solve, but when we write out the characteristic equation, we get this thing, which factors as r minus 3 squared, and it's a repeated root. So I can't do my general a times e to some power plus b times e to some other power because they'll be the same power. And that actually, we actually don't get all the solutions to the differential equation that way. And actually, I need to decide what my independent variable is called. So I'm going to say y is a function of t. Okay. The method we're going to use is actually differential operators. So there was a lecture on this a little while ago, and these didn't necessarily seem useful in a different way than any of the other techniques. It was just another way to see that we could take linear combinations of solutions back when I previously talked about this. But here, this is actually going to help us solve the differential equation in a different way. So we're going to take a very simple differential operator. We'll call it capital D, and it'll just be d by dt. Remember before I was taking pretty complicated ones, I was adding them together and things. Okay, so I can rewrite this original differential equation as this is the second derivative of y with respect to t minus 6 times the first derivative of y with respect to t plus 9y equals 0. And actually, here's an interesting thing. Have you ever wondered why the 2 here is before the y and the 2 down here is after the t? Well, here's why. It's a differential operator. This is, I can write the y off to the side, and then this is the notation for d by dt quantity squared. That's the differential operator squared. So that's why this 2 goes next to the d and this 2 goes next to the t. Thought that was interesting. An interesting thing to think about that all of us have been confused about since Calc 1, basically. So now that notation is demystified. Okay, I've just rewritten this differential equation, and then I'm going to go ahead and sub in big D for d by dt, and it'll look a little bit better. Plus 9y equals 0. I'm going to factor out a y on the right. No, it does matter. It has to stay on the right because the differential operator needs to be applied on the left. Normally I would say it doesn't matter. Totally does. And then because the differential operator is linear, I can factor this like a normal polynomial. So I actually get d minus 3 squared y equals 0. Okay, it doesn't look like I've made this any better. I'm rewriting all this information in a different way. But what this allows us to do, I'm going to leave one of the d minus 3's here, and I'm going to distribute the other one with the y. So this is dy minus 3y equals 0. And why is that good? I'm going to make some other function of t. I'm going to call it u. And I'm going to let that be dy minus 3y. Or in other words, dy is just y prime minus 3y. D just takes derivative with respect to t. Okay, I'm going to call that equation 1. And then notice that since y is a function of t, and so y prime is a function of t, then u is a function of t. U equals u as a function of t. So what happens here? I'm going to sub this out for u. So I get d minus 3 u equals 0. And then I'm going to distribute again. So du minus 3u equals 0. But d just takes derivative with respect to t. U is a function of t, so this is u prime minus 3u equals 0. And now this is a differential equation that we know how to solve. In fact, we'll do exactly what we said at the end of the previous video, which is this is a linear, this is a first order linear homogeneous differential equation with constant coefficients, and since it's linear, the characteristic equation will only have one root, so it'll certainly have distinct roots. The root is 3, so the solution must be some constant times e to the 3t. Okay, now I've solved for u. But remember, from equation 1, u was y prime minus 3y. So now I have y prime minus 3y is a e to the 3t. This is not the nicest thing we've ever seen, but it is something we've seen. This is a first order linear, because it's linear in the variable y. It's not linear in the variable t, but that's okay. It only needs to be linear in the dependent variable. So first order linear differential equation. So we can solve this. Remember, we did this with integrating factors. So we'll do this on the next page. Rewrite out our equation. Y prime minus 3y equals a e to the 3t. And the integrating factor, we took the function of t, which sometimes is a constant, in front of y, right? And we took, so here, the integrating factor will be e to the power of the integral of that, so negative 3 with respect to t. And we can take any antiderivative, so we don't need to worry about constants, e to the 3t, e to the negative 3t. So I'm going to multiply both sides of this by e to the negative 3t. It may have been a minute since we've done this. Minus 3e to the negative 3t y equals, and then e to the positive 3t times e to the negative 3t is just 1. So this is a. Okay, and now we're going to integrate both sides. On the left-hand side, you should find a product rule. In fact, we do. This is the derivative of e to the negative 3t times y. Check that out. Make sure the product rule checks out. And then on the right-hand side, this is derivative of a constant. So this is just at plus some other constant. I'm going to call the constant b this time. So it looks better when I multiply both sides by e to the 3t. So then y equals at e to the 3t plus b e to the 3t. All right, and then that is the solution to our original differential equation here. So that was interesting. When we got repeated roots, 3 and 3, we expected this term. We didn't expect this term. This had an extra t in it. So that's what showed up.